Now let me give you a few definitions first, and then we'll try to, in the entire lecture, do nothing but derive facts like this. So now it's the first time that you've seen three derived facts. Nobody told. AI could derive it. Now all that we'll be doing is making an interesting algorithms that do nothing but derive such a kind of fact. Let's start off with some definitions. So the first one being a model. A model is what is a possible world. So what all propositional symbols do I have? I have honest R1, it can be true or false. I have honest R2, it could be true or false. I do not know. Honest R3, it could be true or false. I also have the others, but let me skip it, otherwise the list will become absolutely too long. And assume that I do not know anything about anything. So I do not know any one of them are true or false. So there are so many possibilities. Like one of them, a possibility could be R1 is honest, R2 is dishonest, and R3 is honest. So this is one model or one possible world. It may be correct or it may not be correct. But a model or a possible world is a possible assignment to true or false to all the entities. Now what I'll do is that I'll start making in constraints now. This was just a bare minimal definition of model. And again, let me just take in three of them. Now let's make a statement. So my statement is alpha is equal to either R1 is dishonest or R2 is dishonest. I made an any statement. Somebody would have called, something would have happened. As of now, I've just made an any statement. Now, M alpha is a set of all models that satisfy my statement, my fact alpha. So one of such models may be, so either of them needs to be false. So let's say R1 is false. Remember, there are more variables. I haven't put that up, true or true. And this is the model M, where R1 is dishonest, R2 is honest, and R3 is honest. It satisfies this, either R1 or R2 is dishonest. So we say M models the statement alpha, or M satisfies the statement alpha, or M is a model of the statement alpha, and M alpha is a set of all such models. So I'm not sure if I can write down all such models, but then I think it may be possible with three. So either this is false or this is false, or both of them are false. And I will repeat it up for the case when so this is a set of all alpha where alpha is not honest R1 or not honest R2. I filled up this table by every possible model. Each row is a model, and I've accounted for all possible model which make alpha as positive. I did not have true, 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 because in that case my statement not honest R1 and all not honest R2 would have been false. These are all the statements such that either R1 or R2 is honest. Now I go on after model and a set of all models M alpha to the most interesting definition, which is what we will be spending most of our time on, is entailment. which says alpha entails beta. So alpha entails beta if and only if the set of all models that satisfy alpha is a subset of all the models that satisfy beta, or alpha is more specific, beta is more generic, or alpha is what puts more constraints, beta has less constraints. Easiest example that you could take is, I say x is equal to 0 is entailed by xy is equal to 0, because here either x can be 0, y could be anything, or y could be 0, x could be anything, or x and y both could be 0, but this one specifically says out of x and y only x is 0. And of course, you've had a look at the same thing in implies. Whenever you write down statements, you always take the generic statement and you always take the specific case of it, and you say exactly the same thing. So what's written is the same old statement that the specifics entail the generics, or alpha entails beta, beta being more specific, and beta is more specific and therefore it has a smaller model, and whenever alpha holds, beta also holds, so that's because it's a subset. So whenever alpha holds, beta also holds. With these statements, let us again take in maybe a very quick example, and my quick example is, again, now this problem has too many variables. I'll still take in 3 of them: honest R1, honest R2, and honest R3. My first statement is, let us say that not honest R1. I know for the fact R2, for consistency, not honest R2. I know R2 is not honest, R2 is false. So a set of all models such that R2 is false, it therefore becomes true, 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 false, false, true, false, false, but this one has to be false. So this is alpha, which is not honest R2. I also taken a second statement, which is a beta, which is, say, not honest R2 or not honest R3. So I make in exactly the same table again, which is honest R1, honest R2, and honest R3. So either R2 or R3 is dishonest. So false, true, true, false, 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 true, true, false, 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 and true and false. And now what you do is this a subset of this? So TFT, TFT, TFF, TFF, FFT, FFT, triple F, triple F. Yes, this is a subset of this. And of course, you anyways knew the fact very well that not honest R2 is a specific case of not honest R2 or not honest R3. By the same example, any one of them could be dishonest over here. Here R2 only is dishonest. So there was really nothing for me to prove. You could have proved that anyhow. Now comes to where do these definitions really lead to. I redefine my knowledge base, and my knowledge base was pretty much defined like this previously, and the same thing goes: not honest R1 or not honest R2, not honest R3, and similarly the other rules. So here this is my knowledge base, which has sentences 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. That's my knowledge base. If I need to derive something more than the knowledge base, if I need to extract out more knowledge from the knowledge base, I'll have to say from my knowledge base, can I derive the statement alpha? That's a new knowledge which wasn't present in the knowledge base, like not honest R2 in the same example. It was a new knowledge. So can I derive a new statement alpha from the statements in my knowledge base? If yes, then this relation holds good, which is, of course, the model knowledge base is a subset of knowledge alpha. And sometimes we would just like to name in algorithms, because all the algorithms that we'll be doing will only be doing this one thing and nothing else. That's the entire agenda for today and the next lecture as well. Algorithms which derive new knowledge, new facts, reason. So that will be the entire aspect of the two lectures. So I might just introduce in the algorithm A here. So I say from algorithm A. From algorithm A is just a caveat. So I like the names of the algorithms. So all we'll do is make these algorithms which derive facts from the knowledge base. Of course, later alpha will be added to the knowledge base. Maybe from there I can derive new facts, new knowledge. Like last time we end up proving R2 was dishonest by so many derivations. Can I derive R2 is dishonest based on whatever is given by my knowledge base? Can I do that? That's entirely what I'll have to do. Now the first algorithm is where we take this very seriously and we honestly do exactly this. Nothing more, nothing less. We do exactly this. We need to find out whether alpha holds or not. We need to find out this. So we generate the entire bulky truth table I showed you over here and the entire table over here, and then we check, okay, whenever this holds good, that's this hold good. One is the subset of the other. So my first algorithm will generate this entire table. Now remember, there were sentences like true, 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 and we did not consider them up because they were false. So I only consider statements which hold in my knowledge base. And similarly for the other one. So whatever I did manually, I'll just write down a extremely small pseudocode of it. Even if I do not write it down, you would be able to do it up. The general name is called as model checking, which is by checking the model you find out if a sentence holds or not. So I say entails is my function. I say in my knowledge base, does the sentence alpha entail or not? Does the sentence alpha entail or not? And of course, what I will do is what I did over here, I'll be making in this truth table. So let us call all these of things as symbols. There were more symbols, I did not consider them up. And I need to generate all permutation and combinations of all symbols. So you could do it by backtracking, of course. So I'm not going to teach you how to generate all permutation and combinations of all symbols. And the permutation and combinations will be stored in a model. So symbols is just honest R1, honest R2, honest R3. And model is the entire entry that you saw, honest R1 as true, honest R2 as false, honest R3 as false. There's just a list of symbols like n queens, column number 1, 2, 3 are just the symbols, and the assignment of it, column number 1, row number 7 is what the model is. We've already seen that up, so I need not explain. All you do is, let's say f is the first symbol in symbols. So I assign f is equal to true and f is equal to false in my model, and f is equal to false in my model, and I recursively call both these things up. So I add this thing in the model, I add this thing in the model. So model union, a new fact added in the model, like in n queens, you add a new assignment to the model. From my symbols, f will get subtracted. Like in n queens, you assign a queen and you just delete it from the set of symbols. Does alpha hold and nothing added to the KB, of course. So entails. Now, both should hold true for my knowledge base to be true. This should also hold and this should also hold, and therefore I have an and over here. And all that this doesn't have is a base condition. So I say if symbols is equal to empty, then now I check if this model, which is all the true and false, if it holds for knowledge base. This also says that last time I used a trick, I should have actually generated the complete table, all trues and false, and then I should cut the one which do not hold. That would have taken a lot of time, but now I'm doing that exactly over here. If, so this else is for this if, and this is a new holds. If the model holds in my knowledge base, then if it holds in alpha, I return true. If it doesn't hold in alpha, I return false. So if it holds in alpha, I return true. If it doesn't hold in alpha, I return false. I just return whether my model holds in alpha. Which is to say, if the entry is there in the knowledge base, is the entry there over here? If yes, then return true. If no, then do not return true, return a false. And the matching else of this, if something is false over here, it's like implication. So if the year is 2025, coronavirus is not going on, completely correct, because the year is not 2025. A entails B can also be understood in terms of alpha implies beta. So I just return a true, which is like cutting the false entries. If I cut the false entries, I don't care whether it's there in my other table or not. I just cut that up. Whatever I was cutting, because it wasn't holding in the knowledge base, I absolutely do not care about it. Now, of course, discussion session, a lot of people have corrected me up. Problems in reading my pseudo-codes. You don't have to read it. It's given in the book. I'm writing exactly the same thing. As well as many people have said you made a little error there. Of course, I'm not expecting you to actually read this code. I'm only giving you things which will help you understand the book. I'm not saying don't read the book. So please read the book for the actual pseudocode. I'm just here to build intuitions. So like I can already see that it's ugly. So the pseudocode is simple. This is my standard backtracking part. So all that does is it makes in this table, including the things which will eventually be cut. And and it makes in the complete table, and this is my base case. So this is the condition of the base case, so let's not consider it up. So first it cuts everything that does not hold in the KB. When it's cut, it just returns true. If it doesn't cut, then it says that okay, something is true in the knowledge base. Now it has to hold in the model alpha. If it doesn't hold, it's false. If it holds, it's true. It entails. One thing that I'll be completely skipping is up. There are so many heuristics that should come into your mind. Like, why didn't I apply this check as and when this was happening? You do that in n-queens. Did anybody code n-queens by saying all n raised to power n solutions and then you check for feasibility? No, nobody does that. Before placing a queen, you check till now everything's so good so far. I could do that here. Of course, I did not do that. Heuristics are up to you. It's backtracking n queens. Current assignment. Can we use minimum remaining value, degree heuristic, most constraining variable, least constraining value? Of course, you should use that. More than encouraged to use that. That is what will make this algorithm better, but the complexity is still exponential. We discuss optimality, completeness, memory complexity, time complexity. It's known. Backtracking, memory complexity linear, time complexity exponential. It is complete. Like your n queens is complete. There are finite set of symbols. N. There are 2 to the power of n entries. The algorithm will fill all of them up. 2 to the power of n entries, and then it will terminate after all to the power of n entries have been generated. There are 2 more properties that we speak about, including all the old examples, BFS, DFS. I skipped them up. One is soundness. So in case of search, soundness of BFS, DFS, uniform cost search is that the path that you are returning, okay. The path that you're returning, okay, but is that path even valid? Or your algorithm is giving a path, so it should be complete, but that path is infeasible. That is what is soundness. We did not consider it up because we were only taking everything valid. Similarly here, we're taking everything valid. So my algorithm will never say, hey, R2 is dishonest, R2 cheated, even though it was honest. That's what soundness. I'll never make in inferences, I'll never make in derivations, I'll never say alpha to be true when in reality alpha is completely false. Now there's another one which is called as grounding. This says that you gave me information, facts, like somebody cheated. Are those facts correct? Or somewhere down the line, there was a rumor that the cheating did not happen. I believed that up and made all my decisions. So that's what is a very related term which is called as grounding. And we will assume that in both search as well as here, grounding is okay. All information that we know is okay, or it's not that the agent is at 2, 3 and it believes it's at 5, 6. And we'll say that because every information that is into my knowledge base, that's into my belief, either I have seen it by my eyes or it has been told to me, not by you students, but by an expert. Only then I'll say that yes, my algorithm is ground. So very quickly again, soundness is nothing but that I say my algorithm only makes in inferences which are correct. If it derives in alpha, it is true that alpha is true. It does not derive something which is may or may not be true. Grounding, whatever it knows, it's ground, it's correct. It doesn't know something which is incorrect. And I guarantee soundness because I see that at every step I searched for all combinations, and by all permutation combinations, I ensure that it always holds. Grounding because I only believe on things which come by an expert, or they come by observing it by my own eyes, assuming my eyes don't lie. Funny thing, sensors are the eyes. There is not even a single sensor that doesn't lie.